Well, thank you for having me. I presume you can hear me all right.
Yes, we can. Thank you.
All right, great. What I would like to do today is tell you a bit about an attribution statement of the climate change impact on Hurricane Ian's rainfall. Now, this is not the first storm we've looked at. In fact, we've looked at probably 30 or more tropical cyclones and hurricanes for examining the effect of climate change on them. As you'll see, it turns out that the effect on rainfall is particularly profound. Can I have the next slide, please? This is my most important slide because it tells you that what I say today are my own views and not necessarily that of the United States Department of Energy, the University of California, or Northern Lawrence Berkeley National Laboratory. It's just me. Next slide, please. So here is Hurricane Ian as it was making landfall and devastating Fort Myers and other towns along the Gulf Coast. It was a pretty big storm, and the impacts were, as you know, and perhaps very painfully know, were large. Can you get the next slide, please? So the damages from hurricanes, and particularly Ian, are really of three kinds. There can be wind damages, which I don't think were as big as the flooding damages for Ian. And I like to divide the flooding damages into two categories. I call them saltwater flooding, which is the storm surge. This is a picture of Fort Myers after a couple of days later. And you can see, that the devastation is pretty intense. But there's also freshwater flooding from the rain itself. And these are really two different processes. This is a couple of days after the storm has passed, and you can see all the sediment that's being dumped into the Gulf from various streams. And so the saltwater flooding is fairly, pretty much, happening in that picture that I just showed you, during the storm, whereas the freshwater flooding may happen a few days later as the rainwater flows through the system of drainage. Next slide, please. So, what does climate change tell us? Well, the wind is an interesting thing. I mean, that is what's driving the storm surge, and theory and indeed modeling tells us that the winds in the strongest storms should become stronger as temperatures increase, and this is because there's more available energy from both the ocean and from the atmosphere itself, from a moisture atmosphere. And so you'd expect that wind damages would be greater and that storm surge would be larger. But what I do is something we call formal detection and attribution, where we're trying to attribute things to human activities. But first we have to find a signal. That's the detection part. And we haven't really found a signal directly in hurricane winds, or at least as measured by or defined by the Savarese-Simpson scale, which is category 1 through 5 way of classifying storms. And that's because it's the way that scale is defined is it's an instantaneous point-wise maximum wind speed. And so it's a noisy field, and this detection attribution is a signal to noise exercise, and the noise is just too large. But I think there, as you'll see, there are some indirect metrics that are suggesting that wind is actually stronger. Next slide, please. So how does it affect rain, which is the topic at hand? And theory, again, tells us that moisture in a fully saturated atmosphere, that's when there's 100% humidity, which is typically the case in a hurricane, increases at about 7% per degree centigrade increase in the local air temperature, or more precisely in the air temperature that's the source of the water, so that in the storm, so that would be the Gulf in this case. And this is known as the Clausius-Clapeyron relationship, and it's an old relationship developed in the 19th century to help make steam engines more efficient. So this isn't rocket science. This is old stuff, and it's very well validated. But what we've shown, mostly through modeling, but a recent paper looks at observations and confirms this result of ours, actually, that hurricane rain increases at a rate greater than this 7% per degree centigrade. And we know this from the study of many previous storms. Harvey was the very first one where we found this. Harvey was sort of, forgive the pun, a watershed event for us because so many three different studies looked at it and came with very similar answers. This is one from Hurricane Maria, which devastated Puerto Rico. A composite storm is shown on the left, showing that the rainfall in the storm is not symmetric around the center of the storm. It has a maximum at about 1 o'clock, I suppose, on this picture, and the amount of rainfall that we estimate to have already been increased by the 1.2 degrees centigrade global warming we have right today. Is sort of in the middle, and what you see there is that that the place where it's raining the most increases the most from climate change, and in fact that's actually true not just in an absolute sense but in a percentage way. And so the change is not symmetric either about the storm, and if we crank up the warming to about 3.5 degrees above pre-industrial levels, which is sort of the worst case scenario for the end of the century, you can see that there's really a profound structural change in the precipitation, that it's much more intense in the center and less in the outsides. And what's happening here, this took me a while to figure this out. This was sort of surprising. I didn't understand it at first. What it really is, I think, is telling us that the winds are actually stronger. And so, what once was a Cat 4 storm, maybe a Cat 5 storm, or it's going to at least be more intense. And so as you look at stronger storms, there obviously are structural differences. And so there's nothing magic, it's just the storm is bigger or stronger and more intense. Next slide, please. So onto that rapid attribution. And the reason we were able to do this is that earlier in the year, in 2022, we had published a paper on the effect of climate change on precipitation during the entire 2020 Atlantic hurricane season. And we did something we called a hindcast, where we forecasted, but after the storm, so it's a hindcast, each individual storm in the season, and we as in a world that was, so with actual temperatures, and we compared those to what I call counterfactual storms, where we reduce the temperature and actually the atmospheric moisture as well, in a world without climate change, estimated from IPCC kind of estimates. And we call that a storyline. So that would have been a cooler world that might have been had humans not interfered with the climate system. And we concluded for hurricane strength storms over the entire season that on average across all these storms, extreme 3-hourly rainfall rates, so that's sort of the peak, increased by at least 11%. And the accumulated rainfall increased by at least 8%. And that, again, around twice the relationship you might expect, or what you might expect just from the thermodynamic effects, this Clausius-Clapeyron thing alone. Next slide, please. So what did we say about Ian? Well, on the 29th of September, which is about a day or maybe a day and a half after landfall, we tweeted. It turns out Twitter is an effective way of communicating this kind of information. We wrote the following, and I'll just read it to you. Using the same attribution technique recently peer-reviewed in Nature Communications, that was the 2020 paper, a preliminary analysis by Professors Kevin Reed and Michael Wehner shows more of the same for Ian. Human-induced climate change increased Ian's extreme rates by over 10%. And the kind of a strong statement, but the key word there is by over. So this is a conservative estimate. Next slide, please. So this is what the factual and counterfactual storms look like. And the reason we were able to do this so fast is we had the codes from the 2020 paper, and we just reinitialized it with the current data from the National Weather Service. And we went to bed. In the morning, we had results, and by afternoon, we were able to make our statement. And so in the world that was, which is the actual storm labeled actual, this is a fairly realistic hindcast. In fact, it's very consistent with what National Hurricane Center actually forecasted the day before or 2 days before. So it's a credible, fit for purpose kind of calculation. And then the one on the left, the counterfactual, is that same thing, only with colder temperatures, especially in the Gulf, but overall. And you can see, even visually, that there's quite a bit less precipitation, rain rather, in the world that might have been than the world that actually was. Next slide, please. So our initial statement was very deliberately conservative. We said over 10%. You got to remember, we did this in a hurry because we wanted it out there, while people were thinking about the storm. And our current statement, which is in a paper under review, actually shows that we were maybe overly conservative. And in fact, we're saying now that our best estimate of the extreme 3-day accumulated precipitation. So this is the places in the over Florida where the rainfall was the highest, increased by 18%. And we put a confidence interval on it for people who are statistically savvy. This is what we call a 95% confidence interval, which is sort of a industry standard for putting bounds on the statement. So our lower estimate is actually 15%, which is, again, quite a bit more than 10. And it's definitely exceeding that 7% per degree centigrade Clausius-Clapeyron relationship on the moisture, because there's only about 0.8 of a degree of attributable warming in the Gulf attributable to human activities in September. And so that puts us about 3 times that thermodynamic scaling rate. Next slide, please. So what next? Well, I've become very interested in this freshwater flooding issue, and we have 2 studies now. Don't have one for Ian, but we have one for Hurricane Ida and Hurricane Harvey. The Ida one is being written up right now, but Harvey, we have 3 or 4 papers on this. And basically, I call this end-to-end attribution of the human influence. We know at the time of Harvey, at that part of the Gulf off of Texas, there was about, for those of you who don't remember, Harvey flooded the greater Houston area because it was a very intense and somewhat unusual storm. There was a degree of attributable warming in the Gulf of that area. That led to a best estimate from multiple papers of about 20% more rain, which led to about 14% more flooding, which is shown in this map here. You can see the world that was is the upper map, and the world that might have been in the South Houston neighborhood is on the lower panel, and it's quite a bit less flooding. It's about 6 feet deeper, in fact, in places where it was flooded. And that 14% more flooded area led to 32% more flooded homes, which is a very large number. This was a storm that NOAA estimated cost about $120 billion. The climate change cost would probably somewhere, a lower estimate, I think, is $14 billion, and a more credible estimate maybe as much as $40 billion due to climate change. In Hurricane Ida, we're really looking at the remnants of that storm in New Jersey and New York and Pennsylvania, where a bunch of people died, mostly low income folks who lived in what they call garden apartments, which is a euphemism for living in the basement. And about 5.5 million people were flooded in Hurricane Ida. And we estimate that climate change caused about 500,000 more people to be flooded than would have been had there not been this human induced climate change. And both of these analyses reveal a profound socioeconomic disparity. And what I mean by that is the people that were disproportionately affected were generally at low income. Next slide. The storm surge, the saltwater flooding, is something we haven't done yet, although we're thinking about it. And with Mithun Deb, who's at the Pacific Northwest National Laboratory in Washington State, this is his calculation. We're thinking about how we might do the storm surge that was compared to the storm surge that might have been. This is his simulation of the storm surge that was, and it's actually pretty credible. But that work is still ongoing, and we'll see where it goes. But it certainly is possible using this same storyline kind of approach given the tools that we have. Next slide, please. So that's all I have. And I presume we're deferring questions to the end of the panel. If not, I can take them.
Yes, we are. Thank you very much, Dr. Wehner.
Thank you.
All right, now we'll be turning to Dr. Michael Savarese.
Hello, everybody. Turn this on. Now you can hear me okay? And can you still hear me when I'm this far away from the mic? Okay, good. Anyway, hi, everybody. Glad to be here. Sorry, I missed the morning. I was in class. Have to, students come first. So anyway, good to be here. I wanted to talk to you a little bit today about hurricanes' impact on the geomorphology of the coast, particularly in Lee and Collier counties. The work is being done collaboratively between the Water School at Florida Gulf Coast University and Temple University. And a lot of this involves some new technology from us. And I advance by the green one. There we go. All right. I'm assuming you all have a sense as to what Hurricane Ian's biography was all about. This is just an image showing it rotating. You probably talked about this morning. This just shows Ian making landfall on September 28th. And as you watch the rotation of the storm, I think you get a sense as to why the storm surge was so intense. In this little cartoon here, on the left, you can see the track of Ian as it makes its way through the Caribbean and into the Gulf of Mexico. And then on the right, you can see the wind history field. And you can see that brown area right where it's making landfall are the areas where the strongest winds are. And because Southwest Florida was principally to the east or to the right side of the center of the storm, we got the unfortunate situation of having the storm rotating in this direction, creating these persistent onshore winds. And because the storm slowed down, because of the strength of the storm, the size of the storm, the potential for storm surge was huge. And of course, the storm surge that we experienced was incredibly devastating, which is really what this presentation is about. A number of you are familiar with some work that's come out of the University of Florida from Peter Sheng's shop, a modeling mapping package called Akun that's founded on some CH3D SWAN modeling. This is actually a hindcasting of the kinds of surge we should have expected given Ian's track and strength. And you can see here plotted here are the inundation depths. They're color coded in feet. They're on the map. And we, from this particular hindcasting, you can see Sanibel was predicted to have 9 to 13, Fort Myers Beach 11 to 15, Naples 5 to 11, and so on. It turns out that in hindcasting mode, when we actually went out and measured the heights of inundation, they did remarkably well at hindcasting what the model would have predicted. So we're fairly confident that this is a pretty good, reliable tool for anticipating storm surge as we move forward into the future with climate change. For this purpose, though, the map just gives you a sense as to where the surge was the greatest, and we're just going to assume that the hindcasting represents reality, at least reasonably well. And you can see where the areas of red are most intense, and they're sitting in and around Fort Myers Beach, Estero Bay, Sanibel Island, not too far off where the worst storm surge was. These are the areas that suffered the most damage, the greatest loss of life, and the greatest property damage along our coast. There's a well-known USGS geologist, Abby Salinger, who in 2000 developed this sort of impact assessment scale. In essence, how well or not so well a coast responds or reacts to storm surge, or a measure of the potential resilience that a coast has to prevent inundation from storm surge, is documented here. And it's really the relative height of the storm surge itself relative to the height of the fortress wall. And the height of the fortress wall essentially is, for all intents and purposes, the height of the foredune, the seawardmost dune ridge, the active dune ridge that sits on our barrier islands and attached beaches. And the height of that dune relative to the height of surge is what dictates how much water gets over the wall and causes the damage behind. Salinger described 4 impact scenarios. A swash scale, you can see the cartoon there on the bottom left. That's where the surge isn't very high and the dune height is more than sufficient to prevent serious calamity. Collision impact, the next one above it, that's where the storm surge is high enough to eat away at the front of the dune and cause dune damage, but not get over the top. Overwash is where the water is literally spilling over the top, and inundation is when the surge is so high that the water passes over the dune as if the fortress wall wasn't there at all. And in essence, given the surges that we experienced and the kinds of damage that resulted, Southwest Florida, Lee and Collier County essentially sat in the overwash inundation impact scenarios for the entire storm. And if you look at these little colored boxes on the right, you can see these are the kinds of damages we should have and actually did experience. We saw extreme dune retreat, the foredune moving backward. We saw dune face erosion very high. And interestingly, because the surge coming in was so high, we actually saw minor narrowing of the beaches. So the beach itself looked relatively unchanged in terms of its width, but in terms of the dune itself and what happened up behind the dune, that's where the action was. And unfortunately, that's the place that's most serious when it comes to compromising resilience of the coast. The beach comes and goes, but once the fortress wall is damaged or changed, then you've got issues. And it's those issues I'd like to present to you in the rest of this presentation. Back before Hurricane Ian, it was actually the spring of last year, FGCU's water school sort of embarked on this process of basically monitoring the coast and the resilience capacity of the coast using, among other tools, a LiDAR-based, a drone-based LiDAR, which allowed us to create topographies or reconstruct topographies to create what is known as digital elevation models. And we started that work, I guess, in a timely or an untimely way. It turns out that we didn't have enough time before Hurricane Ian hit to document the pre-storm condition against which we could compare the post-storm condition. So our work started out where we actually had an opportunity to monitor and map a good portion of the 2 coasts, but not the 2 coasts entirely. And then, of course, the storm hit in September. And so what you're going to see here are sort of pre and post views of what the topographies look like of various places along the Collier and Lee coasts. In addition, we incorporated another tool, something called ground penetrating radar, which allows you to look at the history of storm damage in the subsurface. So one of the things we're trying to do is we're trying to determine whether or not there are genuine hotspots, places where along the coast surge damage is more likely to occur. Those would be the areas that would be most vulnerable as we move forward into the future. From the data, we're able to quantify the amount of sediment that's lost and gained. We're still working on that, but we have the imagery in place. And we're also able to assess, again, the resilience capacity of various coastal segments. The technology that's used, this is Dhruv Butt on the right. He's our drone pilot and GIS, geospatial analyst. That is our former drone. That's a Chinese-made drone that isn't allowed to fly in Florida anymore. We have a replacement drone now. That was an extra $35,000 of investment we hadn't anticipated. But if you look underneath the drone, you can see this big blob of metal that's dangling down there. That's the actual LiDAR radar generator, and then the sensor that captures the reflections. And the picture on the left, that's Ilya Bunevich, my friend and apparently romantic beach buddy, walking, not our dog, but our ground penetrating radar, not here in Southwest Florida, but in the Bahamas. But those are the two tools that are being employed to provide these results. So let me give you an overview of 3 findings. I'm going to give you sort of the punchline first and then show you where that conclusion comes from. The first finding is that this phenomenon known as ebb surge channel formation was prolific. The storm, as it comes in, has an incoming or a flood surge. And it turns out that the surge coming in was so high that the waves are what do the erosion. The waves were sitting so high on top of the surge that those waves kind of bypassed the island on the way in. So the surge coming in didn't cause erosion. It damaged the dune. It moved sand behind the dune. It caused dune deflation, destroyed some dunes, but it didn't create the wholesale erosion that was of the two a more significant impact. Whatever surge goes in eventually has to come out, and that's the ebb surge. And it turns out that the ebb surge was considerably lower, and because of that, it had an opportunity to do substantial damage with respect to wave energy. And that outgoing surge basically cut these deep drainage channels across large lengths of our beach, and it actually incising the deposits that were made by the incoming surge. And I don't have time to show this to you now, but one of the great valuable lessons here, it really matters how you manage the vegetation and human structures behind the beach on the dunes. It turns out that the channels all preferentially developed along devegetated pathways and underneath boardwalks. So places where there wasn't vegetation, either because they were shaded by boardwalks or because the vegetation was removed because of pathway location, that's where the surge channels developed. So we have, at least from this research, an opportunity to think about our management strategies when it comes to providing access across the dune field and onto the beach. And it turns out that this ebb surge channel phenomenon is not new. There are lots of storms that have experienced a similar phenomena. You can see the list there, everything from Hurricane Ike back in 2008, Hugo in '89, and all the way up to Harvey in 2017. So this is a well-documented phenomenon, but frankly, not one that any of us were considering or worrying about in advance of this or any other storm. So let me start showing you some imagery. So in this and in subsequent images, you're going to see maps. The maps are color-coded, and the color codes represent elevations. This is the Tarpon Bay Road Beach, which is right at the southern end, the bottom of the smile that is Sanibel. You can see Sanibel on the inset map. That little green square represents the location of this segment. And what you're seeing here is what the LiDAR-based digital elevation model looked like, not flown by us, but produced back in 2018. This was an area that we didn't fly. You can see the hot colors are high spots, the cold colors are low spots. You can see there's a white, well-developed four-dune ridge running from east to west along Tarpon Bay Road Beach. And when I flip from this to the next slide, you're going to see how that topography changed between 2018 and October 25th of 2022. Okay, so there are the surge channels. You can see they widen to south. So these are, and they deepen to the south. So these truly represent down gravity flows. They must be ebb surge related, water coming off of Sanibel Island, preferentially being funneled through what turns out to be these channels. Again, the channels are virtually unequivocally always located over a path, or where a path used to be. So the paths are dictating the areas of least resistance to the outgoing flow. They have these interesting distributary connections. You can see that kind of branch as you move upward, and the heads of these little channels look like theater-headed canyons. It's as if you were in the Canyonlands on the Colorado Plateau, but in miniature, which is really, really strange and a strange phenomenon. You can, from these digital elevation models, extract profiles. Okay, you're actually seeing a profile through one of these distributary channels. I guess it's the profile number. I can't read my own slide from this far away. 5. Oh, thank you. The one that's all the way on the left, the light blue profile. You go from onshore to the right to offshore to the left, and the light blue represents the pre, and the dark blue represents the post. Okay, you can see there's a difference in elevation here of about 2 meters. That's 2 meters of erosion down into the beach in this one surge canal. So this is the phenomenon, and this phenomenon occurred many, many places, most prolifically on Fort Myers Beach, Sanibel, and Lover's Key, which is what I'd like to show you here. I'm sure most of you are familiar where Lover's Key is. This is undeveloped. It's a state park. In essence, the entire island is mapped here. This was our LiDAR topography flown in May of last year before Ian. Again, reds are highs, hots are highs, and colds are lows. You can see there's a relic dune in red and orange that the park's service has been trying for years to try to restore and rehabilitate with limited success. This is what it looks like before, and this is probably the most devastated island that probably would not naturally restore itself And this is what the situation looks like on October 19th of last year. You can see the surge channels have consumed almost the entire island, and most of that island, at least on October 19th, was subtidal, below intertidal depths. So the channels here are very deep and are therefore influenced by every incoming and outgoing tide. So again, this is the surge channel phenomena at its worst. I'm going to skip that just to save time. One of the things we're able to do, this is just sort of a preliminary analysis that you can do using ArcGIS tools called cut and fill analysis. What you see in red here are places where sediment has been deposited and added to the landscape. And what you see in blue is where material has been removed. So the vast majority of Lover's Key experienced erosion between the pre and post situation. And we're using more sophisticated tools than this to actually quantify that amount, but can't report on it quite yet. I don't know if you've had a chance to see some of these things. If you've made it out to Sanibel, Lover's Key is still closed. There's still channels visible on Fort Myers Beach. Here you can see one on the right from the Tarpon Bay Beach area of Sanibel, and then the one on the left is from Lover's Key. So these are prominent features. And these channels, I should note, pass through the dunes and in many cases extend considerable distance behind the dunes. And on Fort Myers Beach, I don't have any images of this, some of the channels actually underscored and channelized underneath stilted homes that didn't have foundations. So if you had a stilted home, you might have been high enough to avoid the surge, but when the surge channel eroded out from underneath you, it took your home out for that reason. So again, some really interesting lessons to be learned here for management and development. The second finding, everybody talks about seawalls and the value of seawalls. I'm not here to profess support or for or against seawalls, but I'll just show you some interesting observations. There are places along the coast where the seawalls held their ground, and in other places they failed. In Naples, a place where earlier generations of seawalls were unknown and not mapped when they were put in way back, decades ago. The older seawalls were actually exhumed. So new seawalls were destroyed and the older seawalls were eroded out and have created basically a completely new landscape on the coast. Where seawalls were still in place and survived the storm, there was extensive erosion out in front, and you get these deep runnels, deep channels that parallel out in front of the seawalls. So here is Fort Myers Beach, a place that, and this is the central part of Fort Myers Beach. Newton Park is kind of there in the middle. I want to show you two things. In the northwest, the upper left, I'm going to show you the surge channel formation, and that's an area that didn't have seawalls. And then on the southeast, the lower right, a place where there aren't seawalls or fewer seawalls. Excuse me, I got it backwards. Seawalls in the southeast, no ebb surge channel formation, no seawalls in the northeast, lots of ebb channel formation. So here is the northeast. I'll put the arrows up here. You can see the surge channels forming as you drift your eye down to the south towards the yellow arrow. This is where the seawalls are more extensively existing. No ebb surge channel or minimal ebb surge channel formation here. Seawalls pretty much did a decent job, but again, you can see that strip of light blue between the red and the green. That represents the erosion out in front of the seawalls. Here's a photograph of what, I'm sorry, this is the same phenomenon in Naples. This is you can see the pier there on the right, just offshore. This is the pre, and here's the post. Can I back up? I think I can back up. Maybe I can't. In any case, you can see a nice straight line where the yellow hits the green. That straight line is now the exhumed old seawall, and the new seawall was, the more recent seawall was eroded away. Thank you, whoever did that. There we go. Thank you. That was magic. I'm not sure where that came from. Anyway, so seawalls, if they are genuine seawalls and they're holding steady, I guess had significant value, at least at preventing ebb surge. And here's what the phenomenon looks like. You've got a Naples Beach near the pier seawall on the right, a Fort Myers Beach seawall on the left. The Fort Myers one on the left shows the erosion out in front of the seawall. And one could argue that depression is readily managed and easily fixed using just beach nourishment strategies. The third finding, I don't know if you're familiar with strand plains, but there are some portions of our coast that have multiple dune ridges, basically forts with multiple walls, if you will. Multiple walls are a good thing and improve resilience considerably. Geologists call those strand plains. Where we have strand plains on the coast, there was little to no ebb surge channel formation, and those portions of the coast behaved a whole lot better. Okay, this is the strand plain on Sanibel Island, kind of on the western half of the island. You can see all those colored lines. This is the strand plain. Those colored lines actually represent former seawardmost vegetation lines, and they get progressively younger as you move to the offshore. So in essence, Sanibel has been adding these ridges since the 1990s and increasing the width of the fortress, if you will. And so Sanibel, because of its location, has this portion of Sanibel has this tendency to support strand plains, and because of that, it did remarkably well. Here's what the DEM, the digital elevation model, looks like for this portion of Sanibel before Ian, and if you look after Ian, there's one surge channel that appears here, but the rest of this portion of the strand plain remains unscathed. We finished the post-processing for this entire region of Sanibel called Bowman's Beach, and the entire Bowman's Beach behaves this way, so it's not just this one segment. So again, strand plains are a good thing. And when you compare the profiles before and after, they're virtually unchanged. The foredune, the most recent, the seawardmost ridge is affected, but everything behind it has remained unscathed. Okay, so just some food for thought. Maybe there's time to talk about these later. Some management implications. I think this ebb surge channelization, the erosion caused by the outgoing surge, is a formidable issue when it comes to management. This is a very costly kind of an issue. Not only is it damaging the beaches, not only is it damaging the dunes, damaging the fortress walls, but it's doing significant damage to the seawardmost human construction when the houses are built right behind the foredunes. Businesses are right behind the foredunes. It's clear that foredune height is really important. Remember the Salinger analogy, and I would argue that a lot more could be or should be invested in doing dune restoration and increasing the girth and height of the dunes. I don't know what to recommend about seawalls, but I think they're worth seriously thinking about in helping or enhancing resilience, keeping in mind that seawalls do have other unintended consequences that could be triggered by other types of storms. Strand plains are great. Let's help strand plains as much as we can. I think it's not practical to actually build a strand plain, but we can at least keep the strand plains that are already on the landscape healthy and maintain their resilience. And I think it's important to share this kind of information, this, making lemonade out of a sour lemon, this issue of Ian and its impact is a good way to provide very, very useful information when it comes to rebuilding and restoring in our worsening climate. And with that, thank you.
Thank you so much, Dr. Savarese. All right, now we turn it over to Dr. Ernesto Lasso de la Vega.
Thank you. Thank you very much. And I'm so happy to be here and I see so many friendly faces and also very intimidating faces because there's a lot of knowledge here, but they're friendly. I work at the Lee County Hyacinth Control District, and we have this program called Pond Watch. And what I'm glad to see the effects of Ian on the beaches and on the seawalls, also the whole impact. But I'm going to focus on stormwater ponds because that's our main goal, to advise citizens about how to manage stormwater ponds. And that was a big effect on that. And I'll show you that. Well, we put all this data in the Water Atlas. I want to give a nice commercial to the CHNEP, who allow us to put the data there. And we have this whole data collection, all those the black dots that you see there, they're all part of the Pond Watch group. And we have a lot of these. These are last pictures of my volunteers there. I took it at the time when we were having a gathering. Every year we gather and share. But I give a shout to these people because these are the people collecting the data that I'm going to be talking about. I have learned a lot from them. And they're learning, I'm learning. It's great. Okay, so here again, you got enough nice video pictures. I have a still shot here. And September 28th, that's what happened. And in the days after that, this is a map created by NOAA, and as far as the model of how much the rising of the water can affect this area of Lee County. This is the Sanibel view. You see it there. It's mostly in the area of Fort Myers between the Caloosahatchee River and Estero Bay. So I wanted to emphasize and focus now. All the yellow circles are ponds in my Pond Watch program. So it's amazing the data that I have available for this. And we are monitoring their ponds to determine how much salinity is there, how can we advise them, how to help them. And there's been a lot of damage by the saltwater, and I'll get to that. But the white one that you see there is Lakes Parks. Lee County has a Lakes Parks. And I want to emphasize that 7.2, 7.1, those are salinities in November. It was determined in November. The salinities, of course, September, October, November, I went to do this analysis, and there were saltwater in Lakes Park. But then on the right side, you see a tiny little blue ones. Those are neighboring ponds that has been receiving water from a serpentine channels that have been there. The problem here is that it's up to February, and I still salinity 6, 5, 6. The salt has not gone anywhere. It stays there, and it will not go anywhere unless it's moved by other means or by rain. I want to point out too that a lot of newcomers have come out. That's a shark, right, in Lakes Park. There are sharks in Lakes Park, okay? It's dead. Their muscles have come into, and they're attaching to everything. There's jellyfish. You see those yellow circles are jellyfish. So there's all kind of new creatures that have come up along, and they live happily in the saltwater. So consider that as another impact that we have. These are Pond Watchers data. The blue one, very short little buildings there, bars. There are less than 1.2 parts per thousand. And that is the level of salinity that the Water Management District advise not to use water for irrigation when you go above 1.2, because you're going to kill the grass or the plants. All those red bars are definitely higher than that, and some extremely high, 20-something. I mean, that is saltwater, and those are the effects that we were determining before and after the hurricane. Okay, I'm going to focus on this one because many of these will repeat. I'm taking just this one as an example. Sanibel View did we took an aerial picture of that. That's after, you don't see so much damage there, but the pond has been flooded with the water. Before Hurricane Ian on the left, lush, nice, beautiful littoral plants. These ponds are meant to be filtration units, holding units. They were absolutely great in nutrients. The water quality was excellent. The beautiful birds will come in there. It was a great place. Right? Hurricane Ian, saltwater damage, all of those plants. I mean, it was like a nightmare. And it's sad because they worked so hard to maintain the water quality, to maintain this. And now nothing is going to grow because if you see, okay, let me explain something about stratification, because this is what happened. Stratified water, in the surface, you will have warm water. And as you go down in the bottom, on the left of that graphic, you see the depth increasing. So you get colder and colder water in the bottom. That's in the summer. In the fall and the winter, you don't have this. It's called destratified because it mixes. Put that in perspective with the oxygen. Surface water warm, high oxygen, bottom low oxygen, low temperatures. Now add salinity to that. So in this graph, the bar on the blue line shows oxygen. And as you see in the top is high on oxygen. As you go down on the depth in meters, it's become less and less oxygen. It's anoxic. The gray line is salinity. It went from 20 on the surface to 30 something on the bottom. That is a brine down there. There's almost seawater. So and it's stratified, which is a big problem because how are you going to get that saltwater brine down there? How are you going to get it out? There's no way. I mean, this pond's 5 meters. That's a lot of water. Anyway, so that's kind of the problems that we're finding right now. So we are advising them, and I'm going to come on a list. Oh, one thing that we also learned that some plants can survive on this saltwater. In this case, swamp lily, Premium Americanum, is the only one from that same place that they had it and survived. So we're advising for homeowners who have this experience with saltwater to put that plant. Use that plant as a littoral because it's more resistant to salinities. Okay, so the same thing happened in these other two ponds, pond watchers. Again, the water, the oxygen goes down, the blue line is going down, and the salt water goes up. So it's more salty because salt water is denser, it's heavier. And in this other pond on the right, the same thing, drastic stuff like that. But they're in the bottom, they're anaerobic. That means that they're producing ammonia. There's bacteria who are down there, anaerobic bacteria. So you have a serious problem to face now in these ponds. Recommendations. Pray for rain. Oh my God, pray for rain. Because that's the only way to solve salinity, to dissolve salinity is with fresh water. There's no other ways. Chemicals, no chemicals will remove the salt water. Do not irrigate using the pond after water if the water salinities are above 1.2, because again, you kill the grass. And most of these ponds, for my homeowners, they're using it for irrigation. Don't do that. You're going to kill your plants. Just wait. And then determine if your pond is stratified. So those profiles that I'm doing is the answer to see if they are stratified. If they take the surface water, it's always going to be a lot fresher, less salty than the ones in the bottom. You need to find that stratification. If you have an aeration system like bubblers, keep it going because then you break that stratification and you're mixing. But it's dangerous because you can have all that anoxic water in the bottom, mixing it, you kill all the fish. Well, everything is dead there. So, and then the next one, do not turn the fountain. Fountains are not bubblers. They're not mixing the water. They're going to evaporate your water. So do not turn those fountains. Plus, those mussels might sink your fountain pretty soon if you let them be. So fountains is not the solution. Stop the fountains there. And they pump the water out of the pond, preferably from the bottom to an open waterway. I talked to the water management district about this. They say yes. And I talked to Lee County Natural Resources and they say, maybe, depending where they're going to be dumping, we're going to work on a case-by-case base. And I respect that because you don't want to flood somebody else with nasty water, especially salt water. So that is all part of this. And I think it is a good alternative. Now, it costs money. It costs money, and we'll see how this rain, and again, we're monitoring this because that's the part of the story. This is not going to be the first time and only time. It's going to happen again, and we have to have those lessons for the next time. And so I bring this up because as far as the climate change, hurricanes, El Nino, and harmful algae blooms in two subtropical Florida stories, direct and indirect impacts. This was a paper in 2020, if I can read right. Yeah, 2020. Carl Havens was part of this group of researchers. And they already predicted that El Nino and the other conditions will stimulate harmful algae blooms. This is happening right now in my ponds from Pond Watch. The bars that you see light blue, light green, there are before. The ones darker green are after, and most of them increased tremendously because the nutrients, all the runoff nutrients came in there, dying and stimulating algae. And then we were monitoring that as well. And I think that's my last slide with a nice shot of a car, which there are some cars on the water of some of these ponds. So I know that's another story. And I'm done.
All right. Thank
Wow.
you.
Thank you very much.
All right. We're going to go into Menti question and answers. So if you haven't opened up your cell phone or a browser tab, please type in menti.com. You'll be asked to enter a code. The code is 1154-7821. You can go ahead and enter in your questions. And we will turn over to the Menti and read off the questions for our panelists as they come in. All right, we already have. Oh, maybe next one. Sorry. All right, we already have several questions. So we'll start at the top. You want to scroll back up? How do you attribute additional storm deaths, economic impact to climate change? Does it use FEMA flood maps and census tract data? So I'm not sure.
That's for me, I think.
I think so, Dr. Wehner.
Yeah, that's a great question. And the short answer to that is I need to have a collaborator, and I need to have a social scientist. And that's kind of what makes this interesting scientifically is I'm a physical scientist, and collaborating with social scientists who have access to, say, census data and real estate data, combining with our flood maps is how we get to that. We did use the FEMA flood maps for Hurricane Harvey, and we found that 75% of the homes that were flooded were outside of the 100-year FEMA flood level, and thus probably uninsured. We use census tract data for Harvey as well to find that the Hispanic population, the low-income Hispanic population, was disproportionately affected. We also use something from the Centers for Disease Control. It's called the Social Vulnerability Index, which also is a measure of a relative poverty. So the short answer is I need to have someone to work with.
Okay. And then a follow-up question is, so what can we do with this type of information?
Well, that's a good question. I've always believed that knowledge is power. But I think this knowledge leads to some very difficult questions, particularly about rebuilding. You know, if it's a harsh reality that, you know, climate change is continuing, and, you know, I don't see any path forward where we don't have a lot more warming, which means that storms like Ian or any of these other devastating storms, you know, anywhere in the world, are going to be both wetter and with larger storm surges and more wind damage. And so, you know, it's not up for me to decide, you know, what to do. I think that's up to, you know, the general public, you know, through their elected officials and through their actions, to what to do. One particularly interested community, though, is the reinsurance industry, in that you know, they want to price risk appropriately, and if risk from flooding is changing, which, you know, we believe it is, they're going to respond with the way that they price flood insurance.
Great. And we have some other comments over here.
Actually, yes, I got a comment for Dr. Wehner, because definitely when he was presenting, I was thinking about my homeowners. Not everybody had the same problem. Some of them do, and some of it didn't. But I wonder is because the way that the water management district constructed all those canals and the waters, because some of the waters were pushed back, because all the rain that you mentioned, they increased, the tremendous rain that we got, kept a lot of the salt water from coming in. So this is where your mapping will come up perfectly for us to know which communities are in more daring troubles in the future.
That's actually interesting, interesting thought. And this project that I mentioned at the Pacific Northwest Lab that I'm collaborating with, we have modelers there who do exactly this, model salinity in coastal estuarine systems. And we're actually looking at Hurricane Irene right now, because we're focusing on the Mid-Atlantic and the Chesapeake. But it is interesting how the salinity changes during a storm, you know, and it goes in that particular study, that goes up with at the initial part and then comes back down as the fresh water flows through the system. So it's a really interesting and complicated science that I'm only just learning about. It's really, really quite fascinating. I think there's a lot of traction for progress.
And if you don't mind, Michael, I thought I might share an idea about how the information can be used. I think one of the great powers of the attributional science is that if it's documentable, you can demonstrate that the effects we're experiencing in terms of weather phenomena are genuinely due to climate change or anthropogenic forcing of climate change. So it provides a very powerful way for somebody to step back and say, well, you know, a Hurricane Ian is going to hit us, you know, it could hit us at any time in the future. One of the things I've noticed is through community conversations about restoring and rebuilding, everybody's focused on restoring to the pre-existing conditions or trying to build resilience for hurricane-specific impacts without thinking about the exacerbating effects of climate change, sea level being higher, maybe storms being stronger, as Michael noted, storms being wetter because of anthropogenic forcing. I think it's a way to change the conversation, to get people focused on not just being prepared for the status quo, but being prepared for greater impacts in the future. How you communicate that and get that out into the decision maker world is a difficult.
Yeah, thank you for that. You know, you reminded me of something that I probably should have said. And you know, this attribution stuff is an exercise in causal inference or causality. And I'm often, you know, confronted with people who say, well, we've had hurricanes all along. And it's like, yeah, of course we have. What we're not saying that climate change caused Hurricane Ian. We're saying that it caused it to be wetter. And that's an important distinction.
Could I add one more thing? Because I like exactly what you were saying. One simple thing that I'm doing with my homeowners is that collecting the water from the pond, but also their well, because the well is deeper. And I'm determining if the salinities will increase on the dry season or so I'm monitoring that every month. And I show them the graphic here. Look at your well water salinity and keep an eye on that. And now this is the perfect time to show them it is happening. Sorry about that. I get excited about ponds.
Well, I'm going to take a prerogative to piggyback on two things that both of you said. One, the well, I can say from personal experience, I live near a tidal river, and our well water, we started noticing watering our plants that they were starting to get burned, took it in to get tested, and now the salinity of our well water is high enough to start to burn our plants in our yard. So we definitely, over the course of living in that house, are observing directly those types of impacts. And then the other thing is, when you brought up about how much erosion occurred on Lover's Key, Dr. Savarese, we did an analysis a couple of years ago looking at sea level rise and changes that would occur, you know, with low accretion. How would erosion over time and sea level rise affect these islands, these barrier islands? And basically what I was struck with is that we've seen in some of your analysis more of those changes occurring than we had predicted past 2070. So in one storm, we lost in areas more land than we had projected from a combination of sea level rise and other climate factors to be occurring over the next few decades. So that shows us that these things are not going to be like necessarily a slow, steady, but there could be these big events that could propel us forward in leaps and bounds rather than just like at a slow pace. So I think that's something to think about. We have a lot of questions, so I'm going to go through as many of these, several for Dr. Savarese. So I'll go through those. Do you have any updates to share on the Southwest Florida Resiliency Compact? You knew this one was coming.
I knew it was coming. I just didn't think it was coming after this talk. And I also don't want to derail the panel. I'll try to be concise here. So the Southwest Regional Resiliency Coalition is our new name. We still exist, but we're in some sort of comatose state. We actually had a good sort of rallying around, coming together, meeting in September just before Hurricane Ian, and we actually had an agenda for the coming year. And then, of course, Hurricane Ian took everybody by surprise, and frankly, there hasn't been a whole lot of interest in getting together and talk about improving, understanding vulnerability and adaptively planning deeper into the future while people are trying to, recover from Ian. I certainly understand that. So there's nothing new or confidential about that. Maybe the confidential part is I've reached a point where I think I've done as much as I can trying to get the coalition moving forward. What I intend to do, and I had intended to do it already, but haven't done it in advance of this, is just to reach out and ask the group to consider another way to facilitate the organization, because I just don't have the bandwidth to do it, quite honestly. And so I will tell you that the water school, is still pursuing funding, and we still have some irons in the fire to bring in extramural sustainable money to hire someone that could serve as sort of a resiliency officer, resiliency coordinator for the region. Maybe that person, if the funding was put into place, maybe that person could then bring the jurisdictions together and work effectively. Another possibility is to look for another organization to facilitate it. I haven't heard much from county government. I'm not sure what's happening with the Regional Planning Council. If there's any, I heard there may be some change there and maybe some interest there, and maybe some great renewed interest from county government to work with the RPC. And I'm certainly open to suggestions and thoughts. But
Well, I would just add to that I think that this type of event is really important, because policymakers, as we all know, they take their cues from their constituents. So if they see that their voters care about this issue, if we could fill this room and then double this room and start to build, everybody bring 2 or 3 friends next year, we would start to be seen as a more powerful constituency behind this issue. And I think that will translate into policymakers paying attention to this issue, coming to these types of events and wanting to support what we're doing here. But I think it does, there's like a top down, but also a bottom up approach to trying to build this.
I'm happy to talk, at any time. If you have ideas, I welcome suggestions.
Okay, great.
I'm not giving up. I'm just tired.
No. Well, there's nothing wrong. You've done a great job carrying it thus far. So sometimes we just need to continue it's like a marathon, keep passing the torch to the next. Dr. Savarese, your presentation cited a few story maps. Are those publicly available?
Okay. Actually, the digital elevation models that I showed you are not available publicly yet, only because they need to be vetted. They need to be carefully scrutinized before we make them public. But we are working with at least 3 jurisdictions and helping move our maps forward with them. The intention is to make them available. We do have our GIS spatial analyst does have some story maps that overlay the pre and post imagery of the coast, giving you an opportunity to compare photographically anyway what the coast looked like immediately before and immediately after Ian. Those could be made available publicly. I know they're available through ArcGIS software, and I'll talk to my colleague about getting that open to more people and sharing that information. And then eventually the actual DEMs will be shared as well.
Okay, and then we have a couple questions about the strand planes. Can they be implemented in already established areas, beaches, businesses, et cetera, close to shores? And why do you not recommend building new ones?
Okay. Well, strand planes, they're behemoths, they're large. You're not talking about just throwing some sand on a beach, or you're talking about fortifying a dune, but you're building a landscape essentially. And there are certain areas of the coast that have the right process dynamics to allow the strand planes to grow and for those ridges to accrete and increase the width of the island, so to speak. And there are places that just don't have those the right processes. So you can't just, even if you could and you were willing to spend the money to build a landscape that is a strand plane, that doesn't necessarily mean, or probably isn't likely to succeed, simply because the natural processes are not conducive to the strand plane being there. The strand plane is there because nature wants it to be there. So I'm not saying I'm not recommending that strand planes be built. I just don't think it's practical. What I would recommend, though, is that the way you manage development behind a strand plane should be very different the way you manage development behind an area that isn't a strand plane.
Mhm.
So, maybe permitting rules can reflect those differences. Maybe the setback distances can be different. I can tell you that, houses that are stilted and on the oldest ridge in a strand plane would never succumb to ebb surge erosion, given how far back they are, the fact that you've got so many of those ridges out in front of you. And so there are ways to make management decisions and permitting decisions, I think should be considered.
All
There
right.
was
And
another
then
strand plane one in there too.
there is one more about, well, there was one about, what are some alternate strategies to providing beach access without damaging dunes?
Yeah, I also see things about seawalls and living shorelines.
Mhm.
I'm not advocating any one gray or green measure to improve resilience. I think it needs to be considered holistically and comprehensively. So again, seawalls may be great for some things, dune vegetation great for others. The question about how to manage travel across the dune, there's an interesting proposition. I think the EDF people are here, Environmental Defense Fund. There's some emails going back on how to employ dune vegetation and boardwalks in a different sort of way. Whoever thought that boardwalks would be a bad thing, right? Boardwalks were supposed to be what prevented us from damaging the dunes. But in this situation, the shade under a boardwalk is no different than a devegetated pathway because people are walking on it. But if boardwalks aren't straight, if they make two right turns, and if you overlap, this is one of the ideas that the EDF has been floating around, and if you sort of overlap or imbricate the dune vegetation around that dog leg in the boardwalk, now all of a sudden the water doesn't have a direct down gravity path to the Gulf of Mexico.
Or maybe use different materials, like I know that over seagrass areas, they'll build docks out of grates, metal grates, to allow the sun to penetrate, to maintain some sort of vegetation under it. Could build boardwalks similarly, where you allow a certain amount of sunlight to penetrate.
Now, mind you, I'm not an engineer. I've known nothing about the engineering strategies that might be employed here. Maybe these things have been explored and tested in the past.
Mhm.
I'm just learning it myself. So
No, that's great. Dr. Lasso de la Vega, we have a few for you.
thank
Okay.
goodness.
Is there something like Pond Watch in Collier County?
Sadly, no. And in fact, I talked to some people at the pollution control. Pollution control is having the idea, but they don't have the personnel. Sadly.
So there's something that with staff resources, they might be interested. So these are all ideas for you all as citizens in these communities to try to throw some support behind. Does the evaporation in the ponds have the same effect of saltwater aquariums where they get saltier over time?
That's right. It's absolutely true. Dilution is the only solution for that kind of a
For
problem.
that has to be flushed out.
Has to be dissolved, correct? It has to be added more more fresh water into the system in order to reduce the salinity. Yeah.
Okay.
Same as an aquarium.
Do any of the ponds you monitor go down to the aquifer?
They are in the shallow aquifer right now because they were dug artificially. They're dug out and then the water got seepage inside the pond. So they're already connected with a shallow aquifer. Now, deeper, no. So the shallow, yes, there will be some connection even from one pond to another, even under filtering between the soils in between. So that has happened. In fact, I got one case where community was being built and the neighbors all got water sucked out because the community was pumping water and to build that. And it was so sad because the ponds that they build suck the water out of my neighbors. around that community. So that happens all the time. Yeah.
So you explained how that these saltier ponds can become fresher over time. Do you have any time frame? Will it potentially become a dead zone in the meantime? What happens and how long does it take to recover?
That's a very complicated question, but I'll try to handle it in a way that I see it. We're gonna get learning experiences with this rainy season coming up, and we'll see, because I have some ponds that has no aerators, and some ponds who have aerators, and some other ponds that are going to be pumping. So all that experience will be part of our studies. I mean, we're going to learn that experience and to see how we can apply it in the next time.
Okay. Why do older seawalls hold? We think of evolving construction practices as maybe being better, but in this case, we see some of the older ones holding. Is it that there's different materials being used? Do either of you know anything about what might factor between which seawalls survive and which ones fail?
Yeah, I don't have any, call this intuitive evidence. Given what I've seen, there are some things that are called seawalls that really aren't. They're more like just retainment structures. So they're not structurally designed to really hold standing. They're not fortified the right way, and those appear to be the kinds of seawalls that failed. Why in Naples the old ones were exhumed when the new ones were taken away? I honestly don't know. It's just peculiar. I would say, at the very least, it's peculiar that you had this line of seawalls that was essentially eliminated, and then once the seawall is gone, then the erosive capacity increases behind where the seawall was, and that erosive capacity was enough, I would argue, to exhume the older seawalls, but not take them out entirely. So those older seawalls were buried by subsequent sediment, and the erosional capacity of the surge removed that sediment, but didn't take those older seawalls out. So
there's a couple questions related to barrier islands about how it is normal for barrier islands to move according to effects of storms, and why would we be trying to restore them, or should we be changing how we develop on them as a result of what we just experienced with Hurricane Ian? Do you have any thoughts that you'd like to share on that?
I guess I know enough about climate change and sea level rise and storminess and barrier island geology to say that, building on a barrier island doesn't make any sense. So that's me speaking as a pragmatist, maybe as a pragmatist. There's phenomenal science that's been done over the last few decades demonstrating where the tipping points are, what kinds of sea level rise rates, what kinds of stormy conditions need to occur for barrier islands to no longer be stable. And the argument is that our barrier islands are not stable anymore. They're metastable. They are wanting to move. Barrier islands over history, they transgress and they regress. They move landward, they move seaward. As the rate of sea level rise goes up, as the impacts of storms increases, just like Jennifer had mentioned, those events trigger movement of the islands. Lover's Key is doing what barrier islands are supposed to do. You take an island and you cream it with an event with high sea level and intense storm surge, and the island steps back. That's what Lover's Key is doing. At some point, though, sea level rise becomes so accelerated and storms may be so intense and so frequent that barrier islands cease to move and actually drown. You can go out 70 miles off the coast of Naples into the Gulf of Mexico, and there are buried barrier islands on the seafloor there. They're barrier islands that formed at a time when sea level rise lessened about 8,000 years ago, and then sea level rise accelerated to such a high rate during the de-icing of the last glaciation that those barrier islands drowned. Okay, they're there in all of their glory. You can see all the features, but they're on the bottom of the seafloor, something like 60 meters below the surface of the ocean. And so that's the natural tendency. And there are times in Earth history where barrier islands are just not compatible with the rate of sea level rise. And in essence, sea level is going up so rapidly that barrier islands don't even have an opportunity to form. And if you go back about 3,500, 4,000 years ago, before the present, into the interval of time we call the late Holocene, there were no barrier islands then. Okay. And so you think about when the first humans arrived on the landscape, the Calusa or the Paleo Calusa, the predecessor to the Calusa, everybody's been on our coast, at least here in North America, when sea level rise has lessened and when barrier islands existed. So we've never really experienced as a species a barrier island less climate. And again, if sea level does what it might do, I know I'm talking longer and you're eager to get on the next question, but
We have a lot of questions.
So let me just say that was me as the pragmatist. Me as the realist, the other answer to the question would be, it's a wicked problem. How can you tell social scientists talk about wicked problems, problems that are so wicked they can't be solved? How do you tell the people in Fort Myers Beach or St. James City that they can't have their heritage back? You know, you just it is happening, but for a different reason, right? You know, it's because of gentrification and the inability to afford the change. And that's what makes it doubly wicked.
No, I agree. It's definitely more complicated. There's an environmental answer. There's a socioeconomic answer. There's a lot of different things to consider. And I think the level of uncertainty and the timing and all those things, like you said, like how frequent are we going to experience these storms? How quickly will sea level rise? All those things play into it. Whether it makes sense to try to rebuild or to scale back or to even go to managed retreat in some way. But, you know, that is definitely something we'll be tracking over future summits. So there's a couple more pond questions. So I'm going to turn it back to Dr. Lasso de la Vega to talk about how are new ponds put on Pond Watch? Will you select sites based on your own interest and criteria, or can groups and residents apply for their ponds to be added to the research and watch?
Yes, if you are a Lee County resident, this is a program that is the Lee County Hyacinth Control. You pay taxes and you deserve all the service that we provide. So go to the website, Lee County Hyacinth Control District, look for Pond Watch, or find us in the Water Atlas. So we're there. You definitely can be part of our group. And there's another one. It says, has the increase in salt salinity in the stormwater ponds impacted their effectiveness in training nutrients? Yes, it has impacted a lot because they kill a lot of plants. A lot of nutrients went down to the bottom. Bacteria are breaking down those nitrogen in the form of ammonia, which is very dangerous because it does. Anaerobic conditions can really damage the whole pond. It will take a long time, and salinity is increasing that effect. Algae might come later, secondary algae, and then there's all kind of effects that comes from that. There was another one. It says,
and then how does mixing the water in ponds affect the littoral plants? And should communities restore the shorelines before the salinity in the bottom of the pond is back to normal?
No, hold on to the back to normal salinities. At least wait until this spring brings the water and let's see what happened after. And if you're going to be putting plants, put the ones that are salt tolerant. In fact, there's nurseries that are already advising in Sanibel. There's a list of plants that are advising for their ponds in Sanibel because they're really salty there. There was another one that I saw. I want to say that the collective pressure of stormwater ponds, the collective fresh water, is what kept the aquifer at bay in freshwater conditions. It's because all that pressure. Now, if you start reducing the ponds elevation and you start pumping water out of those, then you're reducing that pressure, and you have salt, like your case. Salt water might become, and there's no way to push it back. Once the water, your well is salty, sorry. Because you don't, unless you pump down. Sorry to give you bad news.
All right, we got a wild card one for anybody and everybody. A huge algae mass is taking aim at Florida beaches. What is causing it? Is it climate change?
Not me.
Not me either. Wehner?
I'll throw in something on that. I
didn't know this existed until the drive here.
Oh,
just
really?
before one, I heard a story on NPR. So
no, it's huge.
It's huge. It is.
It's
huge.
mammoth. The sargassum mat.
I do have a comment.
It's enormous.
Yes.
Dr. Michael Wehner, do you have any ideas on that?
Well, I don't actually. I didn't know anything about this, but I would like to phrase the question differently.
Okay.
In not saying climate change causing it, is climate change affecting it? Is climate change causing it to be larger? Is it climate change causing it to be a more frequent event? That would be the kind of question that's answerable
Well,
by an expert on algae masses, which is not me.
yes. Well, I will say that there is some research. I just watched a thing on this about the ocean currents and things are changing. There's warming of the ocean to the point that tropicalization is occurring with whales, temperate whales, moving into areas that were previously only Arctic whales along the east coast of Greenland because the ice sheet no longer comes down and supports like the narwhals. And so we have like humpbacks now in areas that they've never been observed. And they just said even all the way down to the small fish and plankton and things has changed in that part of the ocean. And they said that basically the Arctic is double the warming of other parts of the planet. It's over 3 degrees. And so the ice sheet is deteriorating at a very rapid rate, which is changing ocean currents and air currents around the globe. So it is possible that some of these things that we're observing in other parts of the globe are impacting things that are coming through the ocean towards us. And so that's something I think to be studied, and to understand if maybe that is contributing to the, growth of sargassum. I agree with Dr. Wehner that we have to be careful to not say things are caused. I mean, a lot of these things are naturally occurring, red tide, sargassum, they occur, but do they become exacerbated by climate factors? I think that's the real question.
Okay.
All right, let's see.
Oop.
We have some other questions.
You want me to take the low income one?
Go back up. I think we missed a couple.
Would you like me to take that low income question?
Sure.
Oh, yeah.
Yes, please.
Yes.
This is an interesting question. Now, we haven't looked at Hurricane Ian because I don't have a collaborator who is interested in Florida. My collaborator for Hurricane Harvey is Kevin Smiley. He's at Louisiana State University. He's obviously interested in that part of the world. Now, maybe somebody else might be interested, or maybe he is. I don't know. I haven't asked him. But the impact of climate change are very different depending on your abilities to respond to it. And so the most vulnerable are typically the very old, the very young, the very ill, and the very poor. And so they're usually the least able to adapt, the poorest. But it's not to say that they're always the most disproportionately impacted. In fact, in Hurricane Harvey, we found that, and this puzzled us for a while, that the largest financial damages were the very rich people, and so the richer you were, the greater your financial damage, but also the poorer you were, the greater your relative financial damage was. And the way we sort of understood that is that both groups lived on the water. The rich people lived on the water and had a very nice view, and the poor people lived on the water and probably were looking at a refinery and didn't. And so there's a lot that depends on just the circumstance of where people are living. Now, we also found that there was not a disproportionate impact on the African American community in Houston, but there was in the Hispanic community. And the reason we think that is that the African American community has been there longer in general, and that the Hispanic community are more recent arrivals, and so those people had to live in the areas that hadn't been developed because they were lower and more flood prone. And so it's not always the case that the low income residents are most disproportionately impacted, but it always is the case that those are the people that are least able to recover from it.
No, I think that's a very powerful statement that we experience even here in Southwest Florida, the disparity between some of our inland communities that were very flooded and some of our coastal communities. And while we are happy to report that there's great movement forward in recovery efforts along some of the coastal communities, some of these inland communities, you can see that they haven't really made any progress yet and trying to recover. Maybe they weren't as heavily impacted, but their resources are so much far reduced that they can't even recover from the degree they were impacted. So it's definitely a disparity we see right here as well, Dr. Wehner. So thank you. I want to thank all of our presenters on this panel. Thank you so much.
Thank you for having us.